It's really my great honor to be here. And so this work was done in close collaboration between Alibaba Cloud and ScaleFlux. The goal here is to make the Ali Cloud relational database more efficiently support this kind of, in addition to OLTP, more efficiently support those analytics. So Alibaba relational cloud relational database is called the POLARDB. So POLARDB has compute and storage decoupled architecture, as shown here in this figure. Being a cloud native relational database, POLARDB is well positioned to provide high performance and low cost cloud database service, and is already widely deployed on the Ali Cloud. So actually today, the Ali Cloud has already become the world #3 provider, just after Amazon and Microsoft. So this work really focuses on making the POLARDB better support analytics. So you know that in current practice, in this decoupled structure, that the database nodes handles all the data processing. So as a result, supporting analytics in addition to OLTP inevitably will cause severe contention of resource in terms of CPU, memory, and the network for the database node. So it's leading to a big problems in terms of performance and the cost. So how to solve this problem? It's a very simple idea, is that why not just push down the table scan in analytics from the database node all the way down to the storage node. So it's a very simple idea and has been used already in the industry. So clearly that can straightforwardly reduce the resource contention in the database node and also on the network. But at the same time, it causes the CPU and the memory contention in the storage node. So then we want to further address that issue. Here is another very simple idea. Just why not just apply we call the heterogeneous computing to more efficiently and more cost effectively handle the table scan pushdown inside the storage node, other than relying on the CPU. So the obvious option that has been already widely discussed in the open literature is that we just push down the table scan into a standalone accelerator in the storage node. So the accelerator can be built using FPGA or GPU. And so even though that we call the centralized heterogeneous computing can easily relieve the stress on CPU, it still suffers from memory resource contention and very high data traffic across the I/O stack. And more importantly, for this centralized computing, it is inevitably subject to a compute hotspot because all the data we're just pushing into this single standalone accelerator. So then, even though like maybe people are gonna argue that I can just use peer-to-peer PCIe data transfer, then it can only reduce the memory contention, but still suffers from the other problems, and also it has a higher hardware cost because we need this PCIe infrastructure to support this peer-to-peer transfer. So then very intuitively, a better option is just to replace every solid-state drive in the storage node with a device we call the computational storage drive. So then we inside the storage node, we directly push down the table scan into every single computational storage drive. And then by distributing the table scan tasks over all the computational storage drives, then we pretty much eliminate all the major resource contention and the data traffic across the whole I/O stack can be dramatically reduced. And also, meanwhile, the compute hotspot is gone. So actually, this is an extremely simple, intuitive concept. And so now let's just look a little bit deeper into what we mean by the computational storage drive. So basically, the concept is just we just bring some computation capability into the solid-state drive itself. So here the idea is certainly not new and has been entertained by the academia for over 20 years. And also, really not surprisingly, this idea didn't go anywhere in the real world. And even though on many papers, the people showed very impressive results, but in reality, over the past 20 years, really nothing has been done in the real world. And the reason is very simple. That just given the very healthy CMOS technology scaling in the good old days, it is simply impossible to have a favorable benefit versus cost trade-off to practically justify the use of a computational storage device. And we know that nowadays there is a resurgent interest on this very old concept, computational storage. It is just it's not for any other reason, just because of slowing down of Moore's law. That's it. And actually, even today, when we talk about computational storage, we still should be very, very careful about the trade-off between the benefit and the cost, especially when we talk about the benefit. Like everybody loves to talk about what is a nice feature, what is the benefit of computational storage, but we still should be fully honest to ourselves and to compare any computational storage solution with a CPU-based solution that is truly optimized CPU-based solution. So then we're not cheating to ourselves. Okay, so then really how successful the computational storage can be in the real life essentially depends upon how well we can turn around the trade-off between the benefit and the cost to make it favorable for the real industry to adopt this idea. So to reduce the cost, we have no other options. We have to make the computation as transparent and as unintrusive as possible. And also to improve the benefit, we have to focus on those computations that are fundamentally unfriendly to CPUs. So apparently, the first low-hanging fruit, again, is very simple concept. It's just to make the computational storage drive to support what we call the data path transparent compression. The concept is very simple. The compression is implemented in the hardware on the I/O path, completely transparent to the upper level software stack. So it's really extremely simple concept. And even though it appears to be simple, but really its practical implementation is far from trivial. And right now, we do not have any product on the market yet. So at ScaleFlux, after almost 2 years of R&D, we are releasing such a product in GA to the enterprise market for the first time. So this kind of transparent compression can transparently bring the benefit in terms of both cost and the performance. Just like this IFL results shows, it can improve the random IOPS by over 2 times compared with leading edge NVMe SSD. Actually, it's very easy to understand because by transparently compressing data, we can dramatically reduce the impact of the internal garbage collection. So that is the only reason for that. And at the application level, it can perfectly fit to database. So in addition to seamlessly improving the performance and reducing cost for database, the transparent compression actually brings some very unique and interesting opportunities to allow people to resync the data management software on the higher level. So this is being under active research right now. Okay, so moving step beyond this simple transparent compression, the next step, very intuitively, we just, for this inline data table scan. Again, the basic concept is very simple, just compared with the current practice that we ask CPU to handle everything, computational storage make it possible to push down those routine and tedious data pre-processing, like data decompression and the table scan from the CPU all the way into the hardware. Then we can release the CPU resource, and then the CPU can fully concentrate on those truly intelligent SQL processing. So that can perfectly fit into the picture I showed earlier. That is to help the POLARDB to better handle this analytics workload. So again, it's a very simple idea, and to just push down the table scan in analytics from the database nodes all the way to the computational storage drives inside the storage node. That's it. But certainly, its practical implementation is really not trivial, and it mainly faces two challenges. The first one is that we have to cohesively enhance the entire I/O hierarchy to allow the table scan to flow, to travel through all the way from the analytics engine all the way down to the hardware device. So we have to do some changes along the way to make it possible for the table scan to travel through. Second challenge is that actually in this work we chose the FPGA-based implementation. So we just use FPGA as a device to implement both flash memory control and the table scan processing. The only reason for that is that using FPGA, we can accelerate this development. We can reduce the development cost compared with doing ASIC chip design. Easily can cost like 2 years. But then using FPGA, we can dramatically shorten our development cycle. But at the same time, we're facing big problems caused by the FPGA. For example, the FPGA is way more expensive than ASIC chip. And also, the clock frequency on the FPGA is much lower. And so as a result, because of this lower frequency, we have to use a more silicon resource to make sure that we can achieve sufficiently high performance for the table scan processing. So all these factors make the cost a big problem for us. So to address the two issues, like for the first one, then we just go ahead to do all the kind of modifications. Like first, we enhance the analytics engine to make sure that it can push down the table scan into the POLARDB storage engine. Then for the POLARDB storage engine, given this table scan request, it will convert into a set of information and then further pass this scan request information down to the underlying file system. Then upon receiving each scan request, the file system will analyze this request and then generate the sub request to each individual computational storage drive. And here the data location already converted from the file offset into the LBA. And then it further passes this information down into the device driver. And receiving this scan request from the file system, then device driver will carry out a set of operations in order to make sure that each request can be most effectively served by the hardware. For example, the device driver might need to reorder the scan conditions given some constraint in the hardware. And also, the device driver might cohesively schedule some background operations like a garbage collection in the drive, cohesively together with this scan pushdown request processing. So to address the second challenge and the implementation cost, then we have no other options. We have to improve the FPGA hardware utilization. Then that will allow us to use a relatively cheaper FPGA device. So then for that, we have to improve the utilization of data path pipeline. Like we have to keep all the hardware pipelines as busy, as full as possible. Then for that, we just increase the degree of parallel and the batch processing. So that can really kind of a guideline to guide us how we develop a set of techniques to modify the POLARDB storage engine and optimize our computational storage drive implementation to make sure that we can meet that to improve the hardware utilization. For example, we just use a look-ahead batch processing in the scan scheduling, and also we use both sync and async calls to make sure we can push more data request into the hardware. And also we slightly modified the POLARDB storage engine data block format. And basically we just add a header in the format. But the trick here is that the hardware can analyze the header information to better streamline the hardware processing. So that's it. So then in addition to serving the table scan pushdown, the computational storage node, the computational storage drive also need to serve normal I/O request. So the table on top shows that this computational storage drive can achieve the same I/O performance as the leading edge NVMe SSD. So actually, in order to be a good computational storage drive, you have to be a good storage drive first. You have to deliver a comparable I/O performance with any other NVMe drive. Otherwise, really nobody will use that in the real product. And our drive also supports this snappy decompression and this set of conditions. So in order to evaluate the table scan pushdown efficiency, we extract 6 table scan tasks and from the TPCH benchmark and with a wide range of data selectivity as shown in this table. So here shows our unit test on one storage node. And here the blue and the yellow bar shows that we use we use PCIe, we use CPU in the storage node to handle the data table scan with and without snappy compression. And this red and the purple means like we use a computational storage drive to handle the table scan. So clearly here we show the results show that we can by pushing the table scan into the drive, we can reduce the scan latency and at the same time reduce the CPU utilization. That's really not a surprise. And in addition to that, this figure shows the PCIe and the memory data traffic. Again, that's because we push down all the scan tasks inside the drive. Then we hide all the traffic inside the drive. So clearly, the data traffic in the I/O stack will be reduced. So then we do some evaluation on one POLARDB cluster with 7 database nodes and 3 storage nodes. So this figure compares 3 different scenarios. One is no pushdown. That means the database node handles everything. Second is a CPU-based pushdown. That means we push down the scan into the CPU on the storage node. And the CSD pushdown. That means we push the table scan all the way to the computational storage node inside all the way to the computational storage drive inside the storage node. And the results show that by switching from CPU-based scan into the CSD-based scan, then we can achieve like out of 22 queries, we have 11 queries can enjoy over 30% of latency reduction, and the same thing for the PCIe, PCIe data traffic. We can 7 queries can have more than 50% of data traffic reduction over the PCIe. Okay, so in conclusion, that is we did nothing fancy. We just implement a very simple idea in the context of Alibaba POLARDB. And then today we just present like what we did like to make it happen. It's just cohesively modify the whole hierarchy and to optimize this computational storage drive implementation. And so really, I think as Moore's law is slowing down and the heterogeneous computing is becoming more and more kind of inevitable, we believe that the computational storage drive will play a more important role, it's a bigger and bigger role. And we sincerely hope that our kind of early stage experience will help the industry to better embrace this wave of computational storage drive. So that ends my talk. Thank you very much.
Hi, I'm Umesh Maheshwari from Hewlett-Packard Enterprise. Thanks for presenting the practical trade-offs, the benefits and costs. So 2 questions about the choice of functions to push down.
Yes.
And you mentioned that compression is the lowest hanging fruit.
Yes.
Except that there's some benefit to do compression further up the stack in that you use less of the networking and the PCIe.
Absolutely.
There. So that's one.
Yeah.
The other function you talked about was table scan, and that's, in my mind, a clearer thing to sort of push down.
Yes.
Except table scan, if things are compressed, requires decompression. So you need to do something about
we have to. Yeah, we have
understand
to do the
compression,
decompression.
right?
Yes. Absolutely.
Now there, if you're searching on structured data, the compression being used might be very application specific.
Yes.
Right? So the challenge there is how do you do that with an FPGA, as opposed to some general processor where you can push down a function that will decompress, that will interpret.
Yes, that's a very good question. That is because of the data schema, right? The data schema could vary. So then how we can handle in the FPGA, right? So basically for the table scan, the hardware has to understand the data schema. So actually in our work, in the FPGA, we implement a fairly flexible scan engine that can handle a certain range of different schema, especially because we're specifically working with Alibaba for that POLARDB. So then we exactly know what is the data schema. So then we really kind of customize the engine, but certainly we increase the flexibility to make it possible to support some other slightly different schema. But certainly, you're right, if the schema is completely different, then we have to redesign the hardware engine. And even for certainly if we have ARM core in the controller, then ARM core can help to better reconfigure this hardware engine to analyze, to understand the data. Yeah, but for now, we just fully customize for POLARDB storage format.
Okay, all right, thank you.
Yeah.
Okay, thanks for the interesting talk. And I'm Zhushi from Facebook. So I have one question about the caching things. You know that if we read out the content from the file system to the storage engine or to the analytical engine, we have some cache mechanism there.
Yes.
But benefit from the locality, right? Yes. But if we push down those scan or other queries from the storage engine to the SSD, then we will not have such kind of locality, and maybe we'll have a lot more reads inside the SSD. Yes. So how about address this issue?
Yes, that's a very good question. That's because certainly for the computational storage drive, we cannot touch the cache data already in the cache.
Right.
So in our implementation, that is we first check that whether the big enough chunk of data already located in the cache. If that is, then we just ask the CPU to handle. And if not, then we just push down to our drive.
Okay, so which means inside the drive, you do not do the caching?
No, we do not touch the, yes. So certainly that's, we implement quite sophisticated scheduler. The scheduler based upon now the CPU workload, CPU stress, and whether the data already in the cache, then the scheduler will make the decision. That is whether I'm utilizing the data already in the cache, ask the CPU to handle that, or I would just ask the computational storage drive to do that for me. It's really kind of a dynamic decision on the fly.
Okay, so one question, is that possible to also push down the single lookup, for example, the GET query from the engine to the SSD? Because sometimes GET may benefit more from this offloading because it just needs one item from the whole data block.
Yeah, certainly for the single lookup, I think the problem is that because usually, like in any way, the database will want the whole page back, right, to the database cache, like a MySQL, like in the buffer pool, right? Like I still need to get the whole page back. So then, even though we accelerate the look up, but we still need to send the whole page back to the. So then the gain is, I think, and right now is kind of debatable.
Okay.
Whether that is a good way, but certainly compared with a large chunk table scan, that is much clearly the lower hanging fruit for us to pick.
Thank you.
Yeah, okay.
Nelson Liao from Future Way. I have a quick question about your performance result. Can you turn to that page? Yeah. Yes. Okay. Actually, the quick question is that also there are some people's mention about the low hanging fruit for the decompression. If you look at the CPU based pushdown snappy versus the CSD based pushdown snappy, looks like the performance is kind of like peer in peer. So what's their takeaway for this? That's my first question.
Yes.
Number two question is actually where is the compression being done?
Yes.
Yeah.
Okay, yeah, the first one is a very good observation. Actually, in our evaluation, actually we didn't really throttle the CPU. Like, actually we do not fully stress the CPU. So then, so that is the primary reason. Like because we have plenty of CPU resource to do the decompression. Then as a result, the comparison is really comparable. And for the second question, oh yes, so actually for the compression, it's done by CPU. Yeah.
Hi, Nicholas from Google.
Yes.
You might have answered this earlier with the first question, but do you find that the CSD kind of reduces your flexibility or iteration speed? Like, does it take longer to push new firmware to the CSD versus like writing software?
Yeah, yeah, absolutely. I mean, like to develop this computational storage drive will, so then as I mentioned at the very beginning, like we have to make sure that the computation we want to push to the drive has to be very unfriendly to CPU. And so actually that's the reason why we think the compression is really kind of low-hanging fruit, because the compression and decompression, especially compression, the data processing is really kind of unpredictable, like a random compression will trigger a lot of cache miss. So that will make the CPU-based performance really suffer. And then for that, we just push into the hardware. And also another reason is that the compression is a data independent, like the computational storage drive doesn't have to understand the schema of the data. So really the compression would be the first lowest low-hanging fruit. But certainly like as we move further step by step closer to the application, then well, we need to like which one is better, as you mentioned, like it certainly is easier to write the code for CPU, right? So then we should make sure that the task we want to do is really either unfriendly or not cost effective to let the CPU to handle that. So then for this kind of data pre-processing, so we think that is one good candidate for computational storage drive. But certainly we are still trying to engage with the industry to find out like what other kind of applications that might benefit from the computational storage drive. Certainly the computational storage drive is not a magic wand, right? It really cannot solve all the problems. So we have to make sure that to understand where it can fit best. Yeah.
Thank you.
Sure.
Peter Desnoyers, Northeastern. So, yeah, it has been known for a long time that, if you could put acceleration in storage, it would be great for exhaustive search. However, the history of various accelerators tends to, it's sort of, a lot of things get eaten by smarter algorithms. So to what extent are do you see the problems this is solving amenable to a better index algorithm, basically? Or are these things where fundamentally you are doing more, where it's difficult to get away from exhaustive search?
Yes, that is a very good question. I don't think I have a very good answer for that. We're still on the path to find, certainly for the exhaustive search, I think the best way to do that is really to optimize the software to have a better index, to avoid the exhaustive search. That should be the first thing we try to do. Unless we run out all the options, then we push this computation to the drive. I think for any kind of applications, to optimize algorithm should be the first way, for the first option to think, instead of really kind of, because I feel that sometimes people tend to sell, overhype this kind of pushing computation to the accelerator, to the GPU, to FPGA, to computational storage drive. Sometimes we can be overhyped on that, so we should be very careful.
Thank you.
Yeah.
Hi, I'm Ankush Jain from CMU. I have a question about your latency graphs on the previous slide. Can you go back to the previous slide?
So which one?
So in TS6, you mentioned that it has a selectivity of 100%, and even then you're showing a 20% increase, improvement using FPGAs. I just had a question on why that's the case.
You mean for
TS6?
100%.
So why is there an improvement by using FPGAs in that case?
Oh, in that case, we simply just reduce the CPU usage. That's it. Yes.
Hi, Cheng from University of Chicago. Further on the question about compression, when you are offloading compression to storage, I believe you are transmitting like uncompressed data in the network, right? Is there any trade-off considerations? For example, whether network would be the bottleneck for the cloud-native databases? Would an acceleration service near the compute rather than the storage be a better option?
Yes. So actually, for the drive, we just put the drive in the storage node. So then, actually now, for the networking compression can be done independently by the network. Once we have smart NIC, then the smart NIC can just handle the network traffic compression. Then after that, we just compress locally in the drive. So it's just orthogonal to the network traffic.
Okay, thank you.
Just want to abuse my rights. I want to make one observation, which is that actually, if you look at the firmware of a disk drive, it's incredibly smart.
Yes.
So there's millions of lines of code in a good old-fashioned hard drive just to deal with maintenance of the bits that you store.
Yes.
So there's a lot of computation there. Also, I think folks have compressed onto SSDs for some time. So it's not there are other SSD devices that do compression. But at any rate, I think the work is good. I like the idea of table scan. The other one, is what about aggregation? Have you thought about doing
Yeah,
an
that is what
aggregation
we're
kind of
exploring
functionality?
right now. Yes.
All right.
Yeah. Yeah. Actually, back to the compression effort comment you mentioned that actually the first one is a SandForce. Actually, I have been working with SandForce before. And the SandForce compression is really because that is for SATA drive. And also the SandForce compression is relatively, is basically mainly for their internal GC, not expose the space, and also not for enterprise. But actually for here, we just focus on the enterprise like NVMe stuff. It's certainly, we're not the first one to implement the compression. That's it. That's it. Yeah, that's right.
One last question.
Hi. Yeah, so Juan from Amazon. I have a question about compression, right? So when you push compression down, usually the higher layers are used to know how much space this is going to take, right? So now you're sending this, you don't know how much that you have to feed that back.
Yeah.
And the other question is, when we do this analytic stuff, the database underneath is very large. So are you placing all that in the SSDs or?
So your second question is?
So is the full database stored on the 3 SSDs or computed, or is that coming from somewhere else?
Okay.
So see, SSDs are usually expensive. The database is very big, so.
Yes. Yeah, so actually for the first question, that is really for the application, once we transparently compress the data, actually we have a very simple API, like for upper layer, like for file system, for the application to query, like to understand what is the true physical capacity usage. Because anyway, in today's environment, we need to have a system resource, like a monitoring system, right? To monitor all the hardware system usage. So we just provide a special API to that kind of monitoring mechanism. Then the system will understand like how much the physical capacity has been used. So, and for the second one is really kind of actually the computational storage drive. Actually, back to the previous the comments is that actually the computational storage drive, the most difficult part is not computation, is the storage. So actually, even for our computational storage drive, the cost is very similar to the normal like NVMe drive. So we do not add any much actually like most of our effort spent on the storage, not the computation, actually.
All right,
yeah.
Thanks.
So let's thank the speaker, and let's thank
Thank
all
you
the
very much.
speakers of the session.